I'm Ayus, and this is Covenant CAD, a Bitcoin OP-CAD Covenant simulator built on Starknet. Think of it as Starknet is the brain and Bitcoin Signet is the vault. Here's the problem. Bitcoin can't enforce complex spending conditions today. Script is too limited. OP-CAD under BIP 347 would fix this, but has not been activated. And right now, there is a zero developer tooling to prototype what post-OP-CAD Bitcoin even looks like. So why this matters? Bitcoin holds over $1.5 trillion in value, but almost none of it is programmable. Today, you can send A to B, and that's about it. Post-OP-CAD unlocks conditional spending, automated covenants, trustless vaults, and real cross-chain protocols. Covenant CAD is the developer sandbox for that future. So what did we build? A working prototype. Covenant logic written in Cairo on Starknet, verified by a real on-chain Garage compatible verifier that triggers actual Bitcoin SegWit transactions on Signet. Every single transaction is verifiable on public block explorers. Here's the architecture. Three components. The brain is Starknet Sequoia. It holds the Covenant registry verifier contracts. The hand is a Python node. It watches for on-chain events, constructs and signs real Bitcoin transactions, and broadcasts them. The vault is Bitcoin Signet, a real P2W PKH wallet, real UTXOs, viewable on mempool.space. A WebSocket connection feeds everything to the visualizer UI in real time. The full flow in 9 steps. A user call, execute poll on Starknet. The registry validates the vault, calls the verifier, marks it spent, and emits a poll authorized event. Our Python node picks that up, constructs a SegWit transaction, signs it with ECDSA, and broadcasts it to Bitcoin Signet via Explorer. The UI shows the transaction ID with a clickable Explorer link, end to end about 15 to 20 seconds. Here's the key insight. The Python node is temporary. Today, Starknet verifies the proof, and Python node relays, and Bitcoin moves. There's a trusted layer in the middle. But post OPCAT, Bitcoin script can enforce the commitment directly. No relayer needed. Fully trustless. And our verifier interface is already Garage compatible. So we are ready for that transition. Now let me show you this working live. Okay, now to start with the demo, we can see that the connection is currently lost. Uh, on the top, it says disconnected. This is because we are not connected to the node yet. So let's connect it to the Python node. So as you can see, the node is connected. It says connected to convenient node, and it is trying to fetch the vault. As you can see, it is showing the balance in our Bitcoin wallet, and it also says live signet. So let's check the Bitcoin wallet. So as you can see, it is listed on mempool.space. So I'm trying to show you guys that everything is on the real testnet. And let's also check the Starknet Cairo contract on the Explorer. So as you can see, it is a deployed contract, and we already had some of the function calls previously in the previous testing operations. So okay, now let's start with registering the vault. So we will call register covenant function with vault ID 4 and public inputs as 0x cafe. So this is the execute pool function. Now I will try to explain you what is the call data mean. So 3 is the vault ID, and next 3 is the length of the proof array, and 42, 123, and 456 are the content of the proof array. 1 is the length of the public inputs array, and 0x cafe is the content of the public input. So this is a sample function triggering, which I'm trying to show you guys. Okay, so let's call the execute poll function. So as you can see, it has invoked successfully, and the proof is getting verified. Okay, now the vault is unlocked and transaction is successful. Let's check the transaction on the mempool.space. So as you can see, it is a real signet transaction. Let's also check on the Stark scan for all the contract operations. So as you can see, on the Starknet scan, we can see all our public inputs, proof parameters, and vault ID. So this shows that everything is happening on real testnet. Uh, and it says covenant executed successfully because the logic and proof was verified, and the transaction was successful. As you can see, all the node logs are here. Also, we will try to re-execute the same transaction to show you guys that it is proof against the replay attack, and the application throws an error if we try to execute the same transaction. It says vault already spent. This is not a toy. We have 9 real security invariants enforced on-chain and off-chain. Vault existence check, one shot relay protection, real cross-contract verifier dispatch, proof validation, duplicate registration guards, zero value check, Bitcoin dust protection, atomic crash recovery, and RPC failover, all backed by 5 Cairo unit tests. Here is the roadmap for this application for Q2 of 2026. Foundation and verification. We integrate Garage's full growth 16 verifier, which is literally a one-line address swap. We add real ZK circuits, enable multi-vault concurrent execution, set up CI/CD, and optimize gas on Cairo. The milestone achieved will be real ZK proofs verified on-chain with multiple vaults running in parallel. The roadmap of Q3 2026 would be advanced covenant logic, HTLC integration for time lock covenants, additional spending policies, and multisig and amount limits, vault composition with and/or logic, post-based events replacing polling, and a developer SDK. Milestone achieved will be developers define arbitrary spending policies in Cairo. The roadmap for Q4 2026 is production readiness. Bitcoin mainnet support OP-CAD script template, a decentralized relay network, formal verification of Cairo contracts, and an audit-ready code base. The milestones achieved will be production grade ready for mainnet the moment OP-CAD activates. Thank you. That's Covenant CAD. Real contracts on Starknet Sequoia, real transactions on Bitcoin Signet, all verifiable on Voyager and mempool.space. Thanks for watching.